Inside a ball valve, shutoff depends on one rotating ceramic element that must open, seal, and reopen without losing geometry. Each quarter turn redirects the flow path, so the component at the center carries the combined demands of contact stress, fluid attack, and repeated motion. When slurries contain hard particles or corrosive species, soft sealing surfaces wear first. The ball and its matching ceramic partners are then asked to do more than block flow. They must keep the passage smooth, resist abrasion at the port edge, and maintain stable contact at the sealing zone. Density-stabilized zirconia is widely used where hard particle contact is unavoidable. Typical engineering grades reach Vickers hardness in the low teens gigapascal range, which helps the surface resist grooving, edge rounding, and scratch initiation during repeated cycling. In valve service, that matters at the port lip and along the sealing track. Zirconia is unusual among ceramics because stress can trigger a local crystal transformation near a crack tip. That volume change helps shield the crack and raises fracture toughness compared with many oxide ceramics. The result is a material better able to tolerate contact damage and interrupted loading in mechanical sealing parts. Wear is only one part of valve failure. Corrosion, surface reaction, and deposit buildup can also disturb sealing. Dense zirconia offers broad chemical resistance and does not rust, which helps preserve surface integrity in many aqueous and chemically active streams. Medium composition, temperature, and pH still need review because compatibility is always service-specific. The O-port geometry works through quarter-turn motion. At one position, the bore aligns with the pipeline and the valve opens. After a 90-degree rotation, the solid section blocks the passage and shutoff occurs. That simple movement is why ball valves are valued for fast actuation, but it also means the spherical element must stay dimensionally precise. Leak-tight performance does not come from shape alone. The ball, seat, and stem interface must share a controlled geometry, and the sealing band depends on roundness, lapped finish, and contact load. If the sphere wears unevenly, the contact stress redistributes, torque can rise, and leakage risk increases during cycling. Actuation torque is a system response, not a single material constant. Friction at the seat, fluid pressure across the port, deposited solids, and surface roughness all contribute. A hard, smooth ceramic ball helps the valve rotate consistently, yet the final torque window still depends on seat design, lubrication strategy, and operating pressure. Sizing begins with the valve bore rather than with one universal ceramic-only series. The ball diameter, through-port diameter, wall thickness around the port, and stem drive feature must all match the required flow capacity and shutoff class. O-port designs therefore track the valve envelope and passage area, not a standalone bead or bearing size system. Industrial ball valves are usually discussed by nominal valve size, while the ceramic core is dimensioned inside that envelope. Beyond the main diameter, common custom variables include port size, stem slot dimensions, seat matching radius, chamfers, and relief details. The useful dimension is the assembled geometry rather than one isolated number. In abrasive slurry isolation service, solid particles strike the port edge when the valve moves and then scour the passage during flow. A zirconia ball helps the shutoff element keep its shape under that abrasion, so the closing profile changes more slowly than it would with softer materials. Stable geometry is the first requirement for stable sealing. Slurry lines often combine solids with chemically active liquids. Here the benefit is not just hardness. The dense ceramic passage resists many corrosive environments and avoids metallic rust products, which helps protect flow cleanliness and seat contact. Real service evaluation still needs the full medium description, especially temperature and concentration. Valve components are judged by how quietly they disappear into the process. When wear remains controlled, the passage stays predictable, operating torque stays manageable, and shutdowns for replacement become less frequent. More importantly, a well-matched ceramic core keeps isolating abrasive flow without turning every maintenance cycle into an early surprise.